Oh, it's delicious.
What are you drinking?
It's mineral water. Drinking water on a hot day is like heaven.
That's true. Coke is good, but water is the root of life, so it must be good.
Moreover, it takes decades for water to come out of the water source after it rains in the mountains, right? It's kind of romantic, isn't it?
But even the sun's light takes time.
Yeah, it takes 8 minutes for light to travel from the sun to the earth, right? Indeed, it's romantic to think that the sun we're looking at now is what it looked like 8 minutes ago.
No, the romance of the sun is not like that.
What do you mean?
Today, let me tell you about the greatness of the sun. Let's start with the basic information about the size of the sun. First, let's look at its size. The sun is about 870,000 miles in diameter. That's 109 Earths in a row.
That's crazy.
The similarity ratio is 109 times, so the volume ratio is 1.3 million times. Wouldn't it be great if Mike's savings were 1.3 million times larger?
That'd be $1.3 million.
I'm sorry. Let me get back to the point. It's 1.3 million times the volume, but it weighs 330,000 times as much.
It's a little less dense.
Yeah, because it's made up of lighter elements. Hydrogen and helium.
Hydrogen is the stuff used in hydrogen cars these days, right? The Earth-friendly kind.
It's also Earth-friendly in the sense that it's an energy source for the sun.
I know helium too. The kind that changes your voice when you breathe it in.
Yes. Don't you think it's made of something familiar?
Yes, it is. I wonder why it's made of hydrogen and helium?
To begin with, 98% of the elements that exist in the universe are hydrogen and helium, right? That's why the elements of the sun are more common in the universe.
Oh, really? We don't have all that much hydrogen and helium around us, do we?
That's right. The Earth is unique in the universe in that sense. By the way, the composition of the Earth is as follows.
That's over 60% oxygen and iron.
That's right. I'm going to make a video about oxygen and iron, so please look forward to it. Let's go back to the sun. There is a reason why hydrogen and helium make up almost all of the composition of the universe, because of the origin of the universe. What position are hydrogen and helium on the periodic table?
At the top.
That's right. You know that atoms are made up of neutrons, protons, and electrons, right?
Yeah.
If it's at the top, it means there are fewer neutrons, protons, and electrons. For example, hydrogen is made up of 1 proton and 1 electron, and helium is made up of 2 protons, 2 neutrons, and 2 electrons.
What does that have to do with the origin of the universe?
It is believed that the beginning of the universe was a kind of super huge explosion called the Big Bang. At that time, neutrons, protons, and electrons were flying around in pieces instead of becoming atoms because of the high temperature and pressure. The protons and electrons that were flying around in pieces just happened to bump into each other, and the result was hydrogen.
So, if a lot of these elements stick together, they form various elements?
Well, that's true, but since the universe is expanding at a rapid pace, the probability of collisions is decreasing, and above all, hydrogen and helium are quite stable, so larger elements cannot be created.
Well, then, how are the various elements around us formed?
That's a great question. But I won't explain it in depth today because it's a long story. But there is a hint in the chemical reaction that is happening in the core of the sun.
I think it's burning hydrogen.
No, in the sun, hydrogen is not being burned. Instead, it's converting hydrogen to helium.
You're making another element from an element? You mean like alchemy?
Something like that. When it comes to helium from hydrogen, do you see that the big ball in the middle has gone from 1 to 4? There is a difference between protons and neutrons, though. That's why you can make helium with 4 hydrogens.
But protons and neutrons are different, aren't they?
Yes, that's right. It's not a simple matter of 4 hydrogens coming together. It's quite complicated. Let's take a closer look at the process of synthesizing helium from hydrogen. First, 2 protons are combined to form a proton and a neutron. At this time, neutrinos are emitted.
What is a neutrino?
Neutrinos are subatomic particles that have no electric charge, but don't think too much about that right now.
Okay.
Then another proton reacts with it, and you get two protons and a neutron. At this time, something called gamma rays are emitted. This gamma ray will come out later, so keep it in mind. And then the two react together to form a helium nucleus.
So it's not just the four of them sticking together?
That's right. If you think about the fact that helium is finally formed after many complicated reactions like this, it would be hard to make a larger element, right?
Yes, that's true.
When several atoms come together like this to form another atom, it is called nuclear fusion.
Nuclear fusion, that sounds like nuclear power generation.
Yes, nuclear power generation is fission, and the sun is fusion. Either way, they are the same in that they produce enormous amounts of energy according to the most famous physical formula in the world.
I know this one. It's a famous one.
I'll explain it next time. To put it simply, mass can be converted into energy. And with a very small mass, you can generate a very large amount of energy. I also used a nuclear reaction to generate 1.21 gigawatts of power. In the process of converting 4 hydrogens into 1 helium, only a small amount of mass is lost, 0.7%. Let's do the math for this one reaction we just saw. With this reaction, this much mass is lost.
That's tiny.
And from E equals mc squared, we can calculate the energy produced in one reaction.
I don't know, but since it's to the negative 12th power, isn't that a small amount of energy?
For a single reaction, yes.
There's a lot of these reactions going on, isn't there? I wonder how many of them are happening? I can't imagine it at all.
The mass lost by the sun is 4 million tons per second.
No. Multiply that by the speed of light squared, and what kind of energy is that?
The sun is in trouble, isn't it? The amount of energy the Earth receives from the sun is enormous, but the total amount of energy the sun produces is 2 billion times that. Are you beginning to understand how amazing the sun is?
It's too much, really.
The energy produced by the sun can be expressed in these numbers. You'd be surprised to hear how great these numbers are, wouldn't you?
Well, I'm pretty sure I wouldn't be surprised if you told me that.
It is said that the energy produced by the sun every second is more than the total energy consumed by mankind to date.
What, in 1 second? Oh, I'm surprised. I don't know what you're talking about anymore. I mean, losing 4 billion kilograms per second, isn't that crazy?
It's fine. The mass of the sun is extraordinary. It is said that it will take roughly 10 billion years for the sun to finish its fusion reaction, or lifetime.
I'm full of it.
The sun accounts for 99.8% of the mass of the solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune altogether account for 0.2%. It's just overwhelming.
I can't take it anymore. It's too big. I feel so small.
I've gone a little overboard, haven't I? Let's move on.
What's the next story?
The first story.
You're talking about romance? What's more romantic than water taking decades to come out? I mean, I know the sun is so far away that it takes 8 minutes for light to reach it, but...
Well, yes, it does. 8 minutes and 19 seconds to be exact.
But water is more romantic because it takes longer.
I know it's romantic to think that the water you are drinking now is the rain that fell when you were born. But the sun is not like that, you know.
No, it's 8 minutes and 19 seconds, right?
It's a million years.
What the hell are you talking about?
It is said that it takes a million years for the energy produced at the core of the sun to be emitted as light from the surface of the sun.
Wow! Amazing!
Well, some say it's about 200,000 years, but in any case, we are now seeing light with our eyes from energy that was created as early as or even before the emergence of Homo sapiens.
I didn't know that. I don't know what it is, but I thought it was coming out at the speed of light.
Isn't it amazing? I'll explain it to you. First, the structure of the sun. There is a core in the center, a radiative zone outside that, a convection zone further outside that, and a photosphere in the outermost part.
The core is where the energy is generated, and the photosphere is the part we see, right?
That's right. Thank you for your understanding. The energy created in the core passes through the radiative zone and the convection zone before reaching the photosphere. The radiative and convection zones differ in the way the energy passes through them.
I don't understand how the energy passes through them in the first place.
That's a good question. The energy produced by the sun is in the form of electromagnetic waves called gamma rays. Look again at this diagram you just saw. This is a gamma ray.
Electromagnetic waves are the kind you use in cell phones and the like.
Visible light that we can see is also an electromagnetic wave. Also, infrared rays, ultraviolet rays, and so on. Electromagnetic waves are waves, but they have different properties depending on the fineness of the waves. The fineness of these waves is called wavelength. The gamma rays produced in the center of the sun have very fine waves, and they are in a high energy state. They pass through the radiative zone. The radiative zone is about 400,000 kilometers thick, so at the speed of electromagnetic waves, it would pass through it in a little over a second if it were moving straight ahead. But in reality, we're going to take a lot of detours anyway.
Why?
In the interior of the sun, the protons and electrons in the atoms are separated in a plasma state. The electromagnetic waves interact with these, and they collide, refract, absorb, and radiate, and can only proceed randomly.
It must take a lot of time to go through the thickness of 30 Earths in such a random way.
That's right. After that, it goes through the convection zone that's spinning around and around.
This is going to take a long time, isn't it?
It is said to take hundreds of thousands of years to pass through the radiative and convection zones.
Wow, this is so romantic.
As they bounce off and are absorbed and emitted over hundreds of thousands of years, electromagnetic waves lose more and more energy. In other words, gamma rays become X-rays, X-rays become ultraviolet rays, ultraviolet rays become visible rays become infrared rays, and so on.
Oh, so they all come out as infrared rays?
No, the inside of the radiative zone is random, so some of them come out quite quickly. Those electromagnetic waves come out in ultraviolet light, and over time, the wavelengths can become much longer, like radio waves. In other words, the sun emits electromagnetic waves of various wavelengths.
Surely, it's the ultraviolet rays that give us a sunburn, right? It's infrared rays that make us warm. And we can feel the various wavelengths being emitted. Next time, I'll try not to complain about the heat or the glare.
You're right. The sun is really the only external energy source for the Earth. We should be grateful to the sun. Besides, who cares about the summer heat when you know that the center of the sun is 16 million Kelvin?
Well, that's a different story.
In this channel, we will continue to post videos on topics that make science accessible and fun.
If you find today's video interesting or informative, please click the good button and subscribe.
Also, please feel free to comment.
See you in about 30 years.
Bye.